Macy's.
Thank you. Thank you very much. It's great to be back at IAAC. Yeah, I'm thinking if I should walk, or I'll stay here for now, sitting here because the microphone is here. So I'll, again, great to be here. I'll be quite short, and then so we can have a conversation. Hopefully there's mics that can go around the room. Now, before coming, I had prepared a different presentation. But today we had a meeting at Valdaura in IAAC, up the hill. And I saw some of the more research-based stuff that's happening here. So I decided to focus on something else. What you'll see tonight is very little of what we do in architecture, more we'll do at MIT in terms of research. And then just a glimpse about architecture. If you want, we can talk more about the architecture we do, but you find it also on the usual channels and so on. And so I focus a bit more on the stuff we do at MIT. Now, we were talking with Vicente before about the future. And so I want to show you how people looked at the future in the past. What you see here are some visions of the year 2000 by a number of illustrators in France between 1899 and 1910. And they got something right. For instance, they saw mechanization in agriculture coming, like this. They even imagined at the time Roomba, the little robot cleaning our homes. That's how they imagined it 100 years ago. But also they got a few things horribly wrong. They thought that I would have come to Barcelona using a whale bus, like this one, or that the police could patrol our cities in this way, which even in your wildest drone dreams, you still don't see this coming. The point I'm making here is that the future is open. This is a quote from the great Karl Popper, amazing philosopher, and this in the Method of the Framework in 1994. The future is open, it's not predetermined, and thus it cannot be predicted, except by accident. So they got something right, but there are other things by accident, but something wrong as well. And so the possibilities that lie in the future are infinite. Incidentally, one of the consequences of this by Popper is that we should all be optimists. He says optimism is a duty. And why a duty? Because if the future is open, we can create it, so we can make it better. It's not something that's imposed on us, but it depends on all of us. So then we should be optimistic, and we should have the duty, as he says, of optimism. And then what is the way to build the future? What is the way to turn the present into a future, hopefully a better future? It's design. And I promise is I only had 2 quotes. This is the second one, and then we stop. But he's another amazing guy. It's Herbert Simon. Herbert Simon got the Nobel Prize in the past century. He was a mathematician, a researcher, an economist, a philosopher. He wrote a beautiful book called The Sciences of the Artificial. What the artificial is what we all do. It's this building, it's objects, it's homes, it's what you're doing in all the fabrication that we see here. And he says the natural sciences look at how things are. Design, on the other hand, is concerned with how things ought to be. So design, and what you all do. And that's, for me, is the most beautiful definition of design. Usually, when we do projects in Milan Design Week, I like to, and if there's a presentation, I like to ask people, what's your definition of design? For me, this is the most beautiful one. It's about turning the present into a future, hopefully a better one for all of us. And one of the things we can use is the new condition today that basically allows us to look at the world using data that we didn't have before. The great Ildefonso Cerdà, the father of this beautiful city, in his great book, he writes at some different points in different chapters about he dreams of a day when urbanism will become like a science because of data. And that day has become, and that's this convergence, data with the city. Now, that's just a little bit of introduction. I will not tell you, as I said, very little about the architecture thing, just a few examples, but very little. Also, I will not tell you much about the Biennale. The Biennale is open until 23rd of November, as Daniel mentioned before. I'd love to host you there if you haven't been there. Who's been at the Biennale? Okay, so if you like all the others, if you'd like to stop by Venice by 23rd of November, let me know and we'll have it too. As I said, I will focus more, but the Biennale title is Intelligence, Natural Artificial Collective, how different type of intelligence. At the beginning, I wanted to call it NI. So the time when everybody is so focused on AI, I thought it was important to say NI, how much intelligence we got in nature, and we still need to learn a lot. This new system we call AI are still rather dumb. They're very effective, but still, rather dumb. They absorb a lot of information, yes. They can vomit it when you ask it in different ways, but they're still quite primitive versus the intelligence we find just in the natural world, for instance. But then in the end, the idea was, to do intelligence is spelled like that. It's a common root between the Italian and the English. So we use only one title. Usually the Biennale has two titles, Italian and English title. And we like that intelligence, in Latin, the common root, add this kind of gens, so better gens, as Latin would say, which is about collective, it's about people, it's about putting together natural artificial collective to do what? To tackle a changing climate and a changing planet. If you want, I can tell you more about the Biennale, but again, I didn't want to do, based on your question, if you want, I also have some slides, of course, on the Biennale, we can look at it. But so what I want to do is to show you today how, thanks to data, we can look at different dimensions of cities in a new way. So I want to start with mobility. And mobility, a very old project, one of the first ones we did. That was 20 years ago, the Venice Biennale. At the time, my position this year was by Ricky Burdett, professor at London School of Economics, and the Biennale that year was called about the meta city. And what we did for the first time, something that now it happens every moment, every day in your smartphones, which is looking at data from networks to see how a city, how flows happen in a city. If there's traffic, if people move and so on. That had never been done at the time. Turns out that some actually of the thing we did then, the papers and the patterns and so on, were used in the past, over the past 20 years to do what now happens naturally, seamlessly, every time we open Google Map or Waze or anything else. So you can see this, for the first time, that's we got real-time data from Rome. It was in Venice, the exhibition, but we decided to focus on the Italian capital. We will send that to a proto-cloud we set up at MIT. That summer, you see it there. There was no cloud 20 years ago. And then we would analyze and visualize the data, and then we send it back in real time to the Biennale, to Italy. So Italy to MIT, back to Italy. And I'll show you something like, the visualization from at the time. Then this was, because it was the first time, got quite a bit of discussions. It was at MoMA, the Museum of Modern Art, and so on. This is actually one special day when there was a final of the soccer World Cup. And this is actually Rome. During the final, you see the Colosseum, the river, and this is all the cell phones in Rome moving before the match. You see them, people going here and there. Up there, you see the morning, midday, the afternoon. And then you see before the match, in the afternoon, in the moment, the match begins, silence. Nobody talks anymore. France scores, Italy scores. Halftime, people make a quick call and go to the bathroom. In the second half, normal time, first overtime, second overtime, famous headbutt by Zidane. And finally, Italy wins. A big applause. To the country, not to me. To the winners. Anyway, but over the following year, so we've been using all of this data to discover different things. Here's a recent paper in Nature Cities. By the way, Nature is one of the top scientific journals that they open based on some, also, we were a big part of the process, but they open new Nature Cities that focuses just on the city thing, using data to define what a city is, based on all the flows. A city, cities didn't exist once upon a time when cities emerged 10,000 years ago. They're really a place to bring us together, so that together we can be more than each of us individually, which is what happens in a place like this, in Barcelona, but in IAAC and so on. So here we used all this data to define a city. Or we looked at other things. There's a very famous law that was discovered by this guy called Zip, who was a mathematician in Cambridge, Massachusetts, in the middle of the 20th century. And Zip discovered many things, for instance, a very famous Zip law of cities. But also Zip discovered or worked a lot on something which is called the gravitation law. Gravitation law means that if you take two cities, say Barcelona and Zaragoza, then the flows between the two can be modeled like population 1, population Barcelona, population of Zaragoza, divided distance power alpha, where alpha is an exponent between 1 and 2, which is very similar to the gravitation law, to Newton's law, right? M1, M2 divided by R squared. So he discovered that, but actually by using now this new data, we discovered that there's something more interesting, that if you look at the frequency of space, then you also get a very interesting regularity. So the invariant is not only R squared, but is R multiplied by F squared, which is what you see here on that thing. So At the time, people couldn't measure repeat visits. Now with this data from networks, we can look at how many times we are going A to B or B to A. And then, we discovered this kind of universal law for things. So we actually been able to look at other things in cities. This is something that really bothered me since I was a student in this place. This is Cambridge, not Cambridge, Massachusetts, where I'm now. It's Cambridge, England. And that's a college called Darwin College. It was the old house of Charles Darwin. And as a student, I was in Cambridge, and I was at Darwin College. And I realized I was going from the college to the department, following one route, and from the department to the college, following a different one. And that bothered me, because shortest path, if you're rational, shortest path is symmetrical. A to B equal B to A. So I was consistently inconsistent. And for somebody looking at rationality, that was bothering. So I was, since then, I was saying, well, is it only me, or we all optimize a different way? And so again, looking at new data, this is a paper from 2 or 3 years ago. We looked at 100,000 people, and we all moved, both in Boston and San Francisco. And it turns out we all don't follow shortest path. Which is actually a beautiful thing. What we follow is what animals do as well, which is vector-based navigation. We try to look at the vector, at a goal, a destination, and then we try to minimize angular deviation. And you can imagine that this probably emerged over tens of thousands of years. We were all in Africa, where we're coming from, in the savannah probably, and that optimization algorithm is much easier to calculate. So shortest path is very difficult, and this is good enough. It's not too different, but this becomes non-symmetrical. A to B is not B to A. And then you can see we wanted to probably, our ancestors wanted to save some computational power to look at possible threats from the environment, but this is a good enough thing for doing it. That, as we couple more and more our intelligence with other intelligence, then it's very important to understand how we work. For instance, this stuff does shortest path all the time, but our brain, it turns out, it doesn't, which is what we discovered here. We've been looking at other things. So in this paper, this paper led to the launch of Uber Pool, now Uber Share, because we discovered something in New York. I will not get into detail, but looked at the sharing of rides in New York. If any of you is interested, the paper is this one. All the papers, some of them are a bit mathematics heavy, but they are on the website. We analyzed it, and we realized there was a big potential for sharing rides. You see it here in that graph at the top that you could take in New York. Again, sometimes your questions come from your experience. So in this case, the motivation for this was that many times I was in New York, I was at a hotel, I was going to the airport, and next to me there was somebody else with a trolley going to the same airport. We could have shared a taxi, but we didn't know it. So I wanted to see how many trips could be shared. And so basically, if you look at this, we wanted to look at, with a small delay in arrival, just a few seconds or a few minutes, then we can share a lot of rides, and that's what was published, and then started a nice conversation in the city in New York, and then led to, again, to this collaboration with Uber and to Uber Pool, now called Uber Share, and so on. I will tell you later about what our students now want to do, which is merging this and the sharing a ride in the car with Tinder and Grindr, but that's another story. Anyway, those are some of the papers we've been working on. If you look at the city as well, through data, you can look at other things. So for instance, this is a well-known traffic light. And traffic lights arrive on our roads when cars arrived on our roads, 100 and something years ago. But if you've got an intelligent system, you don't need to stop anymore. You can actually keep on going, just avoiding collisions like this. Don't try it yet. I presented this in Naples, and they told me, so what is new here? Well, I'm Italian, so I can make such politically incorrect jokes, but I've got corroborating evidence. And the former Italian ministers once said that in Milan, traffic lights are instructions. In Rome, they're suggestions. In Naples, they are Christmas decorations. Anyway, also this becomes a beautiful, all of these, by the way, if you think about the question by Herbert Simon, what is design? All of these are, there's a lot of mathematics here, but all these are design problems. This is how you redesign the city, how you can share rights, how you can understand and redesign. So these are design problems, even if they are mathematical, addressed mathematically. So in this case, we use a queuing theory. We rethought the intersection. This is a paper if you're interested, but basically we use this in order to model future intersections that again can be based on a different way that's more similar to what happens in airport. With queuing theory, how you give access in a dynamic way, as we saw before. And and what we do in the office, the office we do different projects. You find them online if you find them on standard channels. But for instance, we did this project with Google where we actually looked at this Waymo, the company Google's sister company, Alphabet, a child company. Waymo does self-driving cars. They run a lot of self-driving taxis now in the US. Can you think about a city where in the morning when you have a lot of traffic, you can use it like this, but then midday you reconfigure it. So we actually develop a robotics, so the same street becomes a place for people, and you decide, when you want cars or when you want to give it to people. This is a competition we won in Paris. It's called Reinventer le Périphérique. Reinventing the Périphérique is a big, infamous ring road around Paris, and the mayor that got the competition about thinking about it in 2050, and so in this case, is about again how you can use it in a more flexible way, how it become a platform for energy, for producing energy as well, and how it allows, if the road is cleaner and safer with electric vehicles and autonomous vehicles, how it can allow us to bridge in different ways, to go back to bridging between two sides. It's almost like a big cut in the city. How can we bridge in different ways? So I want to show this as one-dimensional. Again, we can ask many design questions. We can look at them through mathematics, and we can look at mobility. Mobility is a key part of our cities. We can look at, through data, also society in new ways. For instance, we've been looking at a lot of segregation. Cities, I was saying before, start around 10,000 years ago. And there's a beautiful thing in cities that they bring us together so that we can share goods, we can share ideas, we share chromosomes, and an accelerator of human activity. Together, we can be more than each of us individually. At the same time, we know the cities also divide in factions. That's probably the same thing that happens, probably think about it also in a community, this community, right? By coming together, we can do more, but also there's different groups that then segregate. And again, with data, we can look at segregation in a better way. Segregation today is less visible. With Richard Sennett, who's a colleague and a sociologist, Richard and I have been teaching at MIT for a number of years. We call them liminal ghettos. Liminal because you don't see them. Unlike the past, you see them less, but they're still there. So if you understand them, we can fix it. The image before was from the Porto Biennale I co-created. You can look at this also through the lens of the 15-minute city, which is this paper. Again, if you push the 15-minute city, which is also the super quadra here, is a very good idea. You find a lot of things, but if you push it too much, you got ghettos. You divide the city in ghettos, in villages that don't mix with each other, and that's what we are looking at this paper here. Or we've been looking at other things more related to what happens, to how cities are transforming today in the way we live and work. We all know, not everybody, unfortunately, but many of us can work in a more flexible way following COVID. And the consequence is this is an article we did with, in the New York Times. It's not a scientific one, but we did with Ed Glazer, who's a colleague at Harvard, an economist, about all the empty space in New York you have today. That's the equivalent of many Empire State buildings are empty. You see, this was the other year, but basically you see that vacancies are really, really high in New York. And here we did an experiment that was it happened accidentally. It happened accidentally, and the experiment that usually you can never do. We started just before COVID to collect this data. We went through all the approvals from what is called the Ethical Review Board, at MIT is called COIS, in order to collect anonymized data about the MIT network. You could do the same for the IAAC network. Imagine everybody, every person is a node, anonymous, who the person is, and then if people exchange an email, you put a link between two people, okay? You don't know what they're saying, but you create that as a network science approach. And so we started collecting that, and then COVID came, and it became the experiment that normally you can never do. Because what it does, it takes space, physical space, it removes it, and then it puts it back 2 years later. And so it can allow you to answer the question, what is the power of being together? Which is normally you can never do it, because in the social sciences, you always have systems, you can observe them, you can find correlation, but it's very difficult to find causation. One way to find causation is if you take a variable, you remove it and you put it back, and then you understand the impact of the variable. Normally, you cannot do it. COVID did the experiment with all its tragedy, but did the experiment for us. So we're looking at this. 23rd of March, 2020, MIT goes into lockdown, and look at the network before COVID. It looks like this. So here's MIT. You could do the same here at IAAC. You see different groups, how they communicate, and here you see architecture, computer science, science, art, and so on. And then you get into lockdown and it looks at this. So it's very different, but we didn't know what changed. And so we started looking, network science, look at many parameters, the centrality between us and so on, and we can't find what changed until when we discover something. Now, anybody knows what weak ties and strong ties are? No hands? Okay. But it's just a definition. Think about all your friends. You can put them into two buckets. This is just a definition in sociology. So think about all your friends. Imagine one category of friends is I know person A, I know person B, and A and B also know each other. If you draw it as a triangle, you call it a strong tie. It's a friend who's also a friend of some of the other friends. Okay, so that's a strong tie. But doesn't mean that talk more or anything, but call it just a strong tie. And then sometimes you got people who you know, but they're not friends of your friends. They become a bridge to another community, which is what you see there in orange. And that you just call weak ties. There's a very famous paper from 50 years ago by Mark Granovetter, who's still a professor at Stanford. At the time he was at John Hopkins University, which is called the strength of weak ties. It turns out that if you only have strong ties, we keep on repeating to each other the same story. So I tell you something, then you mention it, and it comes back to me. So basically, it becomes a bubble, right? You know, you're familiar with echo bubbles, so echo chambers and bubbles. So you get that. But usually, the most important information in our lives comes from weak ties, which are the ones that put us in touch with a new community, a different community, the diverse people. You know, is a way to challenge our preconception, to be exposed to new ideas, and so on. That was hypothesized by Mark Granovetter. There's, I think, over 30,000 scientific papers based on his hypothesis, that debating it since then over the past decade. And then, well, you got the story that, yes, so when we don't meet in physical space, like here, then weak ties die. So we talk, we meet on Zoom, but it's usually mostly the strong ties. If you look at this, when you remove the space of architecture, and that's the value of architecture. Architecture is like, think about us like particles colliding and ideas being exchanged. And then architecture does that, and it doesn't happen naturally online. So if you look at this, when we go online at MIT, 23rd of March, 2020, that the number of weak ties go down 80%. And then you see it in the paper, you see it in a moment, if you look at the paper, then when we go back in person, the magic of architecture comes back again. We again meet with each other, we again create serendipity. The key thing is serendipity. You're bumping into people and ideas you didn't know they're not part of your inner circle, which again is the beauty of what happens in a school, what happens here at IAAC. And you see here, when you look at during lockdown, it's almost like a shrinking brain, the MIT campus, and then it goes back to health later. If you're interested, I don't know why it's skipping one. If you're interested, you see it in this paper, again, that's on the website. Or something else we'll be doing is also looking at something like this. Anybody knows who took this video? No? So this video was from a very interesting guy called William White, very well known in the United States in the 1970s and 80s. William White was the first one to take a lot of cameras and go through across New York and look at how people would use public space. Again, look at the power of public space and architecture. So he was going there and measuring all of this and interaction between people by taking this type of movies. By the way, if you've been to New York Public Library and the beautiful Bryant Park, he helped preserve Bryant Park. He was one of the people who, through these videos, managed to do it. And so we got all his videos got hold of all his video. And here we started looking at how we can compare what was happening then and what happens now, with a big difference. If you read his book, at the time he says, collecting videos, he says is great, is easy, he says it's even fun, but at the time he had to annotate this by hand. He had like probably dozens of students looking at frame by frame and annotating and seeing what people were doing. It turns out now we can automate all that with AI. You train an AI system, deep learning, you teach the system to do it, and then you can measure everything on the public space. And then what we did for the first time, this is a paper from 3 months ago, we looked at the places that William White studied in the 1970s and 80s, and then we get contemporary footage of the same places and look at what changed. And that is a paper from from last summer. There's also an article I did about this in The Guardian, if you're interested, more explaining the results. But basically, the thing is that this is, again, the power of being together, but unfortunately, that is changing. And somewhat, in the 1970s, you see people coming together and people going and looking at each other and trying to find friends and making friends in public space. But now public space is becoming more transactional. For instance, we walk much faster through public space than we did 50 years ago. So because, again, we meet people here and then we don't look at it. But that's really the key thing. There's a power of architecture, power of space, so bringing us together. Before we saw it on the MIT campus to develop new ideas, and here in order to make new friends and make new connections. But if you look at this, it's quite striking how in 50 years, public space, which is the glue of the city, since the Agora in Athens, public space is where we all come together and exchange and interact, is changing its function. If we manage to understanding, then as architects, we can start to see how we can improve it. Here are some other papers, but what we are doing in architecture is a museum we designed in Milan that opened recently. Here, we had many different levels. Before us, there was a design by Guy Olenti. You might know Guy did the Musée d'Orsay in Paris. And she had done the interior design, and there were the stairs, but there were only stairs. And in doing the renovation here, we tried to use the stairs as a vertical plaza. You see it better here. And it's interesting because that place, again, is a place to favor people bumping into each other. So again, almost like a plaza, trying to think about how to design new public spaces that favor that interaction. It's the important thing that how architecture can help us to come together as a community, as a city. Or this is a new design for the University of Milan. It's not turning out exactly like that, but the idea was a common ground that will allow people, again, to interact in a new way. This is a building, a skyscraper, a tall skyscraper in Singapore. We finished. It's a collaboration with Big. And if you look at that, it opens out to let nature in. If you look at some of the other pictures, you see in the middle, there's, again, a public space in the middle where people can meet people or can meet nature. Again, how architecture, again, can bring us together in new ways. All right, so that was about looking a little bit about how data can help us see society and then how that can be turned into design. A couple additional things, and then we'll open up for discussion about autonomy. Well, we all know about autonomy. Autonomy is about self-driving cars. Everybody's excited about it. Elon Musk has a $1 trillion bonus if he managed to sort that the problem. But we said, well, let's look at autonomy from a more human point of view, for instance, in Amsterdam. So we're working with the mayor of Amsterdam, and we said, instead of thinking like everybody about autonomous cars, what about thinking about, Amsterdam has a lot of water in the center of these beautiful canals, and the canals were the place where the canals were the kind of the veins of the city where all the main flows were going. If you look at the canal forms in Amsterdam, they all have basically the system in order to get from the barges, from the boats, in order to connect with the houses. So there was a transportation system. And when we go back to the past using self-driving boats, they could move people around, could move things around. As you see here, could sense air quality, water quality, but also become like a dynamic responsive architecture. Think about a bridge, they can self-assemble when you want, or a floating stage. Think about like Archigram, walking city, but it becomes a water, floating city. They can create all these pieces that they can create an infrastructure that's responsive, dynamic, and follows people and the needs of the city. Which, by the way, is nothing new than what Venice did for a long time. There's one very special day in Venice. It's called the Festa del Redentore, where all the gondolas come together to do a temporary bridge. And I think that's a beautiful thing. If you use technology, and I think here at IAAC will play with it, try to use it not necessarily to invent new needs, but try to follow this idea of how to start from things we've always wanted to do, but you can do it in a different way. Paul Valéry said it beautifully. Paul Valéry said, what I want from a modern world is to lead a non-modern life, but in a more comfortable, in a better world. Anyway, I'll show you here how we did this. This is part of an institute we created, which is similar to IAAC. It's called AMS in Amsterdam. So we were part of the founding team with TU Delft and Wageningen University. And here you see, we started with small prototypes. This is what you do. A lot of this here at IAAC, so we this afternoon. We tried different type of propulsion like this, water jets. Now, a few years ago, this would take you a long time. Now you can 3D print it, and in the afternoon, you can put together something like this and test it. These were the first things the first test in 1 to 4, very small here in Amsterdam. I remember that day I told the mayor, well, no worries, even if the research fails miserably, we'll open a toy company, because everybody was having so much fun playing with these things in us. And to do that, again, you need a lot of data. That's a design problem, but you need a lot of data in mathematics. You need to map all the boats. This is what you find on Google on a normal city, but you don't have it on the canal. So there's real-time data in Amsterdam on the canals that you get to map. And then look at how, I think many of you might have a robotic thing like a Roomba or a car and so on using LiDAR. This is how robots, both the boats, but robots in general, look at the world. And basically every second, and you probably have, every second this is called the LiDAR. Every second, we're using LiDAR for many projects to scan the city. Also, if you want to do a 3D model of a building, you use LiDAR. But it's also how a machine looks at the world. It's a very dumb way to do what our brain does. Our brain has two eyes and does real-time photogrammetry to create a 3D model of this space. What the machine does is collect every second, in this case, 300,000 data points. And little by little, you get all the city, all the canals. Which also, this is what allows the boats to move, but it becomes also a way to know much more about the city. So we're also using it to monitor, for instance, quay wall before they fall and other things in Amsterdam. And then when you got all of that, you insert it into an AI system, whatever it is, different type of learning, but that's the input, and then you teach the system how to behave. So this is the MIT swimming pool. That's what people use swimming pool for at MIT. And then you teach the system to avoid obstacles. Simple obstacles like this, or very complex ones. This is Wei. Wei was promoted full professor after this, no, assistant professor after this. He's an amazing researcher, but he's now a professor in Michigan. And you see here how the system avoids obstacles and so on. And if you're interested in some of the papers, it's a great paper, again, that Wei did. And this is actually, if you come to Amsterdam, I'll take you on a tour on the canals.
It's Lucy. Lucy is a rowboat, a fully autonomous, zero-emission boat that operates on urban waterways, and she can change the way cities work. As congestion and emissions continue to rise, while cities continue to grow, the existing infrastructure of many cities struggles to keep up. Rowboats offer a solution by moving road traffic to the water. By bringing passengers from A to B, or as an on-demand boat, taking you anywhere you want. And they can also help the city as a multi-purpose workboat. Take Kristen. She is equipped to collect household waste to free the streets from heavy garbage trucks. Rowboats are fully autonomous, so they navigate without a skipper who can operate 24/7. In order to sail by themselves, rowboats need to perceive their environment and recognize objects such as bridge pillars, floating objects, and of course other vessels. The primary source of information comes from a LiDAR sensor, but rowboats are also equipped with cameras, GPS, and a digital compass. Rowboat's onboard computer combines and processes all of the data and runs the rowboat software so it can successfully complete its mission plan. After 5 years of development, testing and experimentation, we have now successfully enabled autonomy on the full-scale prototypes. Rowboat is ready for the next step. Join us and let's unlock the potential of urban waterways together.
Oh, sorry, apologies about that. I clicked inadvertently, but it was over. So that's by the way also became a little company, a robot that now is scaling this up for cities. Most cities, it turns out, they're close to bodies of water, like Barcelona, close to the sea, or lakes or rivers. So that's being scaled up. And to finish, clearly one important thing is how we can use data to better keep track of our environment. You can look at this car with the LiDAR on the top. So you see there is the same LiDAR we saw before. But a car like this also has thousands of sensors. Like this is mapping of those sensors. And then you can use it as an ambient sensing platform. Or for instance, to monitor infrastructure. Some of you might remember this was a collapse of a bridge in Southern Europe a few years ago. But many bridges have a collapse all over the world. Anybody knows which bridge this is? No, generally previous one, but this one?
This is by the
No, this one is the Tacoma Bridge, and if anybody has done civil engineering, you've seen this was the first bridge where this was filmed and actually helped humanity understand that bridges, suspension bridges like this one, when there's a lot of wind, they start resonating, and then this thing collapses. So since then, the way we design bridges is different, and the lower part is much more rigid to avoid this kind of torsional instability that people, engineers, hadn't thought about. And it happens when you got wind. But I'll tell you another story about this bridge. This bridge is called Longfellow Bridge. It's a bridge to the left, you got the beginning of the MIT campus. To the right, you got Boston. And I used to walk on this bridge several times a day until when they realized it was about to collapse. So it had to be rebuilt. For several years, Boston and Cambridge were disconnected in one direction. You could only go from Cambridge to Boston on this bridge, and then it was a longer route on the other side. So a huge cost for the city, monetary cost. And the reason is that the bridge wasn't monitored. So that we discovered too late that it has basically to be rebuilt. And today, to monitor a bridge, you can put sensors or send people, but in both cases, it costs a lot of money. And so our idea was, what about getting the same data? Data is usually about vibration on the bridge in a different way. Your phones, cars, or accelerometers like that one can actually measure accelerometer and gyroscopes in the phone, vibrations. And so we put that on the car, and we decided to start with this bridge. That's the Golden Gate Bridge. Why this? Because we know everything about it. In scientific terms, you can say we've got a lot of ground truth. We know how it behaves because there's so many people monitoring that we can check our data against data collected from the ground. And so we took a car and started going around the Golden Gate, back and forth, 100 times. After 100 times, the San Francisco police got very suspicious, so we were stopped. But by that time, we had collected all our data, the data we needed. So you see it here, and it turns out that yes, you can use this to monitor infrastructure. And then this opens up to a beautiful thing. It's the first paper we did. You find it online. But we also work with Uber again to get data from the Uber app. And then what you can do is just, if you have a partnership with an app, you could monitor a whole country with very little cost because you get all this vibration data and you can use it to get a stability of the bridge. This also led to a company, a spin-off. One of the people working on this at MIT then was from Politecnico di Milano, and there's a company he's now running, involved partially in turning this again into a startup. Or we've been looking at how we can put sensors on moving things. Sensor becomes smaller, cheaper, so we put sensors on track. These are garbage trucks in Cambridge, Massachusetts. We call it City Scanner. And so basically, only 3 garbage trucks. You'll be surprised how much data they can collect about the city. We developed a kind of modular system. And so basically we can scan, we move things, and in doing that we also discover, I mentioned before, 3 garbage trucks, and you get data high resolution for every city in Cambridge once a week. So we got interested in the mathematics, and if you're interested, we discovered something cool that basically you need very few vehicles if you want to scan up to 50% of a city. You see it in this paper, here you see these curves are very similar to what you find in chemistry about saturation curves. You see how vertical is the beginning. The x-axis is the number of vehicles, the y is the percentage of streets of the city you are scanning every day. And look at like New York, you've got many cities in the US, in Europe, and in China. But if you look at New York, for instance, if you want to scan 50% of the cities or the streets in New York, then you need a very small number of vehicles. You see it here, this is a logarithmic scale no, it's not logarithmic scale, no, this is linear, but basically just a few dozens of vehicles, you scan, you get data from at least 50% of the streets in New York every day. And now we're looking at other things. We got interested in, our cities are filled with fiber. That's the fiber allows us to communicate. It's everywhere. And it turns out, with colleagues at Stanford, we could turn the fiber into like a microphone. It's called DAC, distributed acoustic sensors. And then you can do the same thing that people do in geophysics. So I don't know how familiar you are with geophysics, but in geophysics, what you do usually, geophysics is a way, well, the geophysics is a broader term. But when you're doing geophysics and you're looking at the structure of the Earth, one way to do it is that you generate some waves, usually with dynamite, and then you put a bunch of microphones, and by looking at how all you know the wave you're generating, you look at how they get to the microphones, you can know what is reflected and refracted underneath, and then you can make the structure of the Earth. So the way everything we know about the Earth underground is usually done with something like that. You generate some waves and you measure how they propagate. Now, in this case, we are using the fiber is what is called geophones, so which is you measure the waves, and you can look at, here is the thing, again, there's quite a bit of mathematics. This is a paper from just a month ago. From 6 months ago. But what you see is that how we can get this kind of sensing, almost acoustic sensing system for the city. In San Jose, we show that this tells beautiful information, no privacy implications at all, but beautiful information about anything, and also preventing, for instance, cracks in buildings. You manage it. The resolution of this is so high that you can look basically at human steps as they move to the city, but it can tell you, a lot of additional things about the city itself. And we've been looking also at the dirty side of the city. Anybody knows which map this is? Yes, you said yes, but you said, what is it?
This is the John Snow map of the...
Well done. Big applause. So this was John Snow's map. What's the name? Huh? Yosa. So applause to Yosa. So John Snow map, why is it very important? So this is a map that started epidemiology in the 19th century. So John Snow discovered with this map, so through the study of the city, he discovered something super important that saves millions of lives from the point of view of epidemiology, because he discovered basically how cholera is transmitted. What he did, he went to Broad Street in London and looked at the wells and the cases of cholera. And at the time, people didn't know how cholera would spread. Some people thought it was through the air, through interactions, through different things. But then he realized it was through water, because all the cases of cholera were clustering around wells. So it meant the well was polluted, and then that all the population around the well would get cholera. So inspired by that, we said, what about today doing something similar? And we decided to go and see what we can get into sewage water. Now, you know that in our bodies, we are kind of meta-organism. In our body, for every cell in our body, we got kind of 9 or 10 viruses and bacteria living with us. It's what's called a microbiome, the human microbiome. In the human microbiome is, you can measure it, you can send a stool sample to some of the companies, they will tell you that, but you cannot do it yet in real time. It's still too expensive, too difficult. But if you do it at an aggregated level, like in the neighborhood, we can get a microbiome of a small community, and then we can do it almost in real time, different times a day. So we designed a little robot to go into sewage to collect samples, do some of the measurements. This was the first robot, this is the second one. Some of the measurements are done locally. It's called Lab on a Chip. In many of these projects, we collaborated with other people at MIT. The one on robots was with computer science and artificial intelligence. In this case, we collaborated both with computer science and artificial intelligence to design these kind of little robots, but also with biological engineering at MIT. So here you see the two little robots, and then you get the data, you sequencing. Sequencing is what is basically the same thing that happened during COVID. You will look at a piece of DNA to see if you had COVID. In this case, you can also amplify everything, and then you don't find just a target, but you do what is called metagenomics. So more generally, omics means that you're looking at all the pieces of DNA, RNA, and also different molecules that you have in this case into sewage thing. And then you need to study the thing, but you study this is the sewage system in Cambridge. But here you see a little video, and this actually again tells you a lot about health at the local level, can help you control epidemics. a company came out of this. We did the project before COVID, and BioBot that came out of this was the main company doing COVID surveillance in cities, which means basically instead of doing lockdown in the whole city, you may see that COVID is only one part, and then if you detect in one part, you can just do lockdown and something off in the whole thing. You will see here in the little video. So as you can tell, we like to get this is a paper if you're interested, but get our hands dirty. So I'll finish with this project, also getting our hands dirty. And here in this project, we started from again, usually start from the things, the experience in your daily life. In this case, something that bothered me for a long time is that if you look at this computer here on the table, today you know everything about this computer. You can go online, you see every chip, where it was produced, how it moved on the planet, how it became this machine. But then a few years from now, you stop using this computer, you sell it, at some point somebody will throw it away, and then you don't know anything anymore about it. Sometimes this is what happens to a lot of the waste we produce. And so the idea was, how could we understand that better? And so we started many years, there's different phases to this project. The next one will happen at the Olympics next year, the 2026 Olympics on the Alps, the Winter Olympics. But as we started developing little tags to put on waste and to follow waste. The first one we designed was here to the left. It's like a miniature cell phone that we created. With a difference, your cell phone sends a lot of data for little time, for one day. This has to send very little data for a long time, for months or even years. And then here is the paper. We did a first deployment years ago in Seattle. We had 500 volunteers. They came with 3,000 pieces of trash. We put a tag on all of them, from banana peels to electronics. And then after tagging all of them, we started throwing them. So here you see 3,000 objects the day of deployment in Seattle. After a few days, you see some of the main landfills next to Seattle. But actually, how far stuff started to travel. Nobody expected it. Look at the trace that went all the way to Chicago, changed its mind, and went back to California. We thought the Faraway Symphony was a good choice for the music. Anyway, so from that and then this was the first experiment. We had a second experiment a few years later, and then we looked at just e-waste globally. The first one was all the United States, as you saw. Then we looked at global flows, and we discovered places such as this one in the middle of the jungle where illegal waste was going. Hopefully that has been fixed now. Anyway, this was made public, became a documentary, a series, not a series, but a documentary by PBS in the United States, the TV. And you see here, this is all e-waste from the US. This is all electronic. Some of the traces are legal, some are not. And then going both to Asia and to Africa on both sides, and tracking it, again, discovering stuff. But again, knowledge can help us then design a better system. Again, this is a design thing. You get the knowledge, and then you try to fix it. In this case, the design goes through regulation, through trying to get to fixing some of the loopholes we got in the regulation today, but basically it is that. And then in a here finish, we also discover, again, next year we are going, now with this engineer, I tagged is super cheap, biodegradable, and want to use it in thousands at the Olympics in next year in the Alps, the Winter Olympics, I was saying. But I want to finish with something else totally unexpected we discovered. And we discovered it when a burglar, came to our lab at MIT. And this guy came and installed a lot of things for our lab, including some of the tags and computers that tell you where they go. And this is what happened. All right, thank you.